Welcome to the third year class. We mentioned that each year of the program has its priorities. We usually start out with basic electricity, so the priority in basic electricity this year will be to get you involved now. Instead of a DC circuit, we're going to get into an alternating current circuit. And you're going to see that instead of only resistance, which you have in a DC circuit, now, you'll see that when we get into a changing magnetic field as we have in an alternating current circuit, you're going to see that now we have another opposition to current flow. In a DC circuit, you have only resistance. Now, when we get into alternating current circuit, you're going to see that we're going to have opposition to a current flow in the form of reactance. In other words, an inductor and a capacitor will offer a reactance to our circuit. This reactance is another opposition to current flow. In other words, now in our alternating current circuits, we're going to not only have resistance, but we're also going to have reactance. And we need to understand reactance in our circuits. You want to go into it with an open mind, and you'll find that it won't be that difficult. It'll be interesting, in fact. In fact, you have to understand this when we get into impedance and power factors of circuits. To understand your capacitor banks, you have to fully understand the circuits as we will now know them. Now, besides circuits, what we want to do is get into transformer connections. And we'll go into great detail. I'll take each of the transformer connections that you will be working on or have worked on, and I'll come in close on them with a camera, and then we'll work them out together. I think you'll see this will be a great help to you. Now, let's go on with our circuits. What we want to do now is do a little review on the effect of a resistor in the circuit. Now, you've worked with resistors, and of course you've worked with them in series and parallel and in combination. In other words, series parallel. Let's go back and do just a little review with the resistor, and then we'll bring in another component. Now, in your DC circuits, we represent a DC circuit by a single cell like I have here. We put a resistor in that circuit, and it looked like this. Now, if I was to energize that circuit, if I had a switch in here, and I would close that switch, the amount of current flow that I would have flowing through that circuit would be dependent on the value of my voltage and the value of that resistance. In other words, the current flow that I would have would be the current is equal to the voltage divided by the resistance. They're going to be directly proportional, you see. Now, we represent that resistor by the symbol R. If I was to energize that circuit, let's say this is a zero voltage plane. If I would energize that, in other words, close that circuit in, you would see that my voltage across that resistor would cause the current to jump right straight up to whatever value of current would be drawn by that circuit. Then it's going to be the same throughout. Now, the value of current that I would have right here would be dependent on the voltage and the resistance. If I had 100 volts applied to that circuit, and I had a resistance in resistor 1 now of, say, 10 ohms, I would have then 10 amps flowing through that circuit. In other words, it'll instantaneously jump up to that 10 amp value. Now, we've worked with circuits in series and parallel, and we'll get into some other circuits later. But now I want to change this and introduce another component. An inductor in the circuit is a coil. sometimes maybe referred to a choke coil. But a coil tends to oppose any change in the current flow. And I can draw a schematic symbol of an inductor by putting coil in here, just like that. In other words, this would be my inductor in that circuit. It's a coil of wire. The value of that coil, that inductor I should say, the value of that inductor can be changed. I can increase my number of turns, I can make the turns more compact, I can stick a piece of iron in there that'll concentrate the flux rate within that inductor. All of those variables will increase the value of that inductor. The symbol that we're going to use for an inductor is L. Remember, we use R for a resistor. Now for an inductor we're going to use L. Now the unit of measure of that inductance now is going to be a Henry. We get an inductive effect measured in Henrys. Now, that inductive effect of 1 Henry is created in our circuit when a change of current flow of 1 amp per second yields 1 volt back on itself. Now, if I get a change in the current, we said that this inductor opposes a change in the current flow. The way it does that is that if I have a change in the current flow, that means that I have a change in the magnetic field around that coil. Now, if I have an effect of the change of the magnetic field around that coil actually induces a voltage back on itself. Because the turns of wire are wrapped close to one another and I've got a changing magnetic field, that means a changing magnetic field. I have flux lines cutting itself. That in turn creates what we call a counter electromotive force, or sometimes referred to as a back voltage. Now that back voltage is opposite in direction. The thing to remember is that a coil or an inductor, a transformer has a coil to it. Those coils oppose any change in the current flow, and the way they do it is by creating a counter electromotive force back on itself, or back voltage sometimes it's referred to. Now, if there is no changing magnetic field, then there is no opposition to that current flow in the form of that inductor. The resistance of the wire would be the only opposition to current flow if there's no change in the current flow. That's important to remember. Now, we have, if we put in this circuit now, we're going to still use DC now. I'm going to show you the effect of this coil in a DC circuit. If in this circuit I put an inductor, and remember that's our symbol for an inductor, and remember that that symbol is L, the unit of measure of, in other words, the inductive effect I get from that is measured in Henrys, and the symbol we're going to use for that is a small h. In other words, if I give you a value of an inductor in Henrys, I'll use a small h behind it. See? Now we'll call this L1. We have an applied voltage onto this circuit. Now here's the thing that's important to remember. If I draw, say, a level line here for zero current flow, like I did for that resistor, and we're going to put a switch in this circuit just like we did for that resistor, and when we close that switch, we said that the opposition to current flow created by that coil in that circuit was going to cause a counter electromotive force, which in turn is going to hold back our current flow. In other words, it opposes a change in the current flow. The way this would look, if I close this switch in, is that the current flow, because I'm getting a changing magnetic field, the minute I close or the instant I close that switch, what's going to happen, my current flow is going to try and build up to a maximum, but because of the induced counter electromotive force, it doesn't instantaneously go to the maximum. It'll go through what we call time current curves till it reaches its maximum, then it levels off at maximum. Now once it reaches that full value, it's just like taking that coil of wire and straightening it out. All it sees now is the resistance of the wire itself. That resistance in turn would determine what the maximum amount of current flow would be at this point. You see? So this is important to understand. We get an opposition to a change in the current flow created by that inductor. Okay? Now, let's go one more component and put a capacitor in the circuit. Now, the symbol for capacitance, we're going to use two plates like this. And this is a schematic symbol now of a capacitor. The unit of measure now of a capacitor is in farads. And we're going to use well, I'll write it out, farad. This is a farad. Okay. Now, a farad, we'll use F for a farad. The symbol for a capacitor will be a C. We're going to use, we said R is a resistor, L was an inductor, C is going to be a capacitor. This unit of measure of capacitance is ridiculously high, you might say. In other words, a farad is a tremendous size to it. So you're going to see that in most cases, in all cases, anytime I mention a value for a capacitor, you're going to see we're going to be using prefixes. Now, we use prefixes in the first year of the program. You use it in the second year of the program in your circuits. So you can see the importance of those prefixes. In fact, most of the time we're going to be dealing with a microfarad. You'll see that if you were to get into, if we were to work on a lot of circuits, a lot of times maybe something as small as a capacitor that might be in a radio or something like that, they would probably be a picofarad or a microfarad, if you will. So the farad is a considerable size. If I was to compare, or to give you an idea of about what a farad would be, you'd be talking about 1 farad as being, say, 2 plates that are probably 6.5 miles square, spaced out with air between them at 1 millimeter. Now, what is a farad? A farad is when a quantity of electrons, and we're going to use a coulomb again. Remember we said that 1 coulomb was equal to 6.28 times 10 to the 18th power electrons. Now, what a farad is, if I get that quantity of electrons deposited on those plates with 1 volt applied to it, then I have a 1 farad capacitor. So most of the time we're going to be using using prefixes. Now, we can change the value of that capacitor in any of one of 3 ways. We can change the distance between the plates. In other words, the closer they are together, the larger the value of capacitance that I'll have in farads. I can increase the size of the plates. Another one is I can change the dielectric material that's between them. Now, capacitors, you can see that I've got a capacitor drawn here. Capacitors are going to have a dielectric material placed between those plates. Now, there's a standard there, and we compare that to air. Air has a dielectric constant of 1. If I had a dielectric material that had a value of 2, it'd have twice the capacitive effect as air. Now, we're going to work with capacitors. We're going to work with capacitor banks and so on. It's going to be important that you understand the effect of a capacitor in the circuit. Now, underground cable has a high capacitive effect in comparison to overhead lines. Overhead lines, you have a capacitive effect there. It's quite small. It can be large, but if I say, for example, have my conductors closer together, and of course there's air as a dielectric material, they're going to give me more of a capacitive effect than if I had them spread out further. So I do get capacitance on an overhead system. On an underground system, you can have such a tremendously high capacitive effect that it increases the load in your circuits. And of course, this is getting way ahead of the game. When we get into our circuits, I'll bring this up again. So we can change the value of that capacitor in any one of those 3 ways. If I was to show you a capacitor in a DC circuit, it would look like this. We would have a capacitor with the DC applied to it. If I put a switch in this circuit, it would look like that. Now, the effect that I would get from that capacitor in the circuit is going to be just the opposite of the effect that I get with the inductance in that circuit. We said if we had an inductor in the circuit, it would oppose a change in the current flow. 1 amp per second would give me 1 volt counter electromotive force. That would be now at 1 Henry. So there's a completely different opposite effect to the two. Now we get an opposition to a change in current flow from an inductor. We're going to get an opposition to a change in voltage now from a capacitor. Just the opposite effect. And that'll be important to understand, particularly when we get into where we start applying it to our circuit. You're going to see that if I have a high inductive reactance, I can add capacitors to cancel it out, you see, and then cut down my load in my circuit. We're going to be doing work like that. Okay? Now, with my circuits, now we have gone through and we've dealt with resistors. And we said that with a resistor now, in my circuit, in a DC circuit, what I'll have, if this is my zero current flow, that when I energize that circuit, it instantaneously go to the maximum, and then that'll be my current flow. Okay, if I put an inductor in the circuit, we said that what's going to happen there is that it will tend to oppose a change in the current flow, so it takes it a while to get up to the maximum, and then we'll have our current flow. In other words, then it's going to look just like a resistor. Now, that inductor, you see, when we get a changing magnetic field, it's inducing back on itself. It's holding back any change that that current flow is trying to make. It can't go to the maximum because it's going to induce a counter electromotive force to oppose that thing. Now, we talked about how there was time constants that it took to get up there. We don't want to dwell too much on that. In fact, I don't test at all on that. I think, however, it would be good for me to go through and explain what we mean by time constants. In your books it talks about time constants and so on. In other words, the value of that inductor will determine the rate, in other words, how long it will take for it to get to the maximum. It'll go through 5 time constants. Each time constant is going to take so long. Now, the length of time that it takes for a time constant is equal to the value of the inductor divided by the value of the resistance in that circuit. So if I have an inductor, the value of that inductor is in henries divided by the resistance, which is in ohms. And I can find out in seconds just how long it's going to take for it to get to that maximum value. Now, if I have an inductor and a resistor in that circuit, those combined values are going to determine what my time constants are going to be. Now, the first time constant is going to be a value of 63.2% of the maximum value. The next time constant is going to be 63.2% of what's left. The next time constant is 63.2 of what's left from there. So you see what's going to happen. It's going to go through 5 time constants. And of course in the book they give all the percentages for that. If I was to de-energize that circuit after it reaches its maximum, what'll happen, it'll go through the reverse procedure, only this time it'll go through time constants to decay down to 0 again. Now they call this stored energy. Once the magnetic field around the wire is built up, or the coil in this case, once it's built up, and you de-energize it, or you shut it off, you open the switch, what'll happen, it'll collapse down around. In other words, when I open the circuit, the magnetic field collapses, so it's like stored energy. And of course, because you have a situation where it's opposing a change in the current flow, it's trying to go to 0, but it can't go down there instantaneously because of the counter electromotive force again built back on itself. Now what it'll do, it'll go through time constants again till it gets to go through 5 time constants again, all the way until it gets down to 0 again. Now what it does, it goes to 36.8% of what the difference is between full value and 0. The next time constant will be 36.8% of that until it goes through 5 time constants to get back to 0 again. So from the inductor, we're getting an opposition to a change in the current flow, and we can represent that by a curve like this. In other words, if I had DC in my circuit, it will build up slow like this. If I have capacitance in that circuit, here's my 0 current flow. What happens now here is we get a sudden rush of current flow till the capacitor gets charged, and then after it gets charged, then it blocks the flow of DC, and it will look something like this. So you get the opposite effect from an inductor and a capacitor. And remember now that when we start going through our circuits, we'll have our circuits. Our circuits is what you've worked with so far. We're going to have L circuits. We're going to have C circuits. We're going to have RLC, RL circuits, and so on. You identify the circuit by the components that are in it. And of course, what we want to do is apply this to alternating current. But before we do that, we want to go through the methods that we use to say add or say parallel or series connect our inductors and capacitors. Now you remember that with resistors in the circuit, that what we did was to add the resistors in series, right? In parallel the resistors, we use the reciprocal method. With inductors in the circuit, we're going to treat them the very same way. With inductors in the circuit and they're in series, I would take their inductive effects and I would add them together. In parallel, I would use the reciprocal method for those values of inductors to find their totals. And I'm going to work some of these out to show you. For a capacitor, we use just the opposite effect. if the value of the capacitor is indicated and in series, I would use just the opposite effect. And I'll show you why. In other words, when they're in parallel, I'll add them. When they're in series, I'll use the reciprocal method. So let's work some of those circuits. Now let me show you how you'll treat the three components in a circuit. When we started out with DC, we said the only opposition to current flow that you had was resistance. And that if we had resistors in series, now this would be end to end, if we had resistors in series, that we would add them together to get our R sub T, our total resistance. Now if I had resistors in parallel, what I would do there is to use the reciprocal method to find their totals. In other words, if I want an equivalent resistance of those two, I would have to use the reciprocal method to get it, if they're in parallel. Up here, they're in series, I would have to add them together to get the total. Okay? Now, if I had, let's say, inductors in here instead of resistors, I'll put inductors in there. And I want to find their totals. I would treat them just exactly like I did the resistors. In other words, my value of my L sub T in this case, L sub T in both cases here, would be L1 plus L2 when they're in series. And then when I have them in parallel, I would have my L1 and my L2. I would use the unequal branch or reciprocal method, whatever the case might be. So you'll treat the inductors just exactly like you did the resistors to find your inductance total in either case. Okay? Now let's take a capacitor. Now you'll treat those just the opposite. If I have capacitors in series like this, to find my total capacitance, my C sub T in this case, what I would have to do now is use the reciprocal method. And the reason for that is when I put them in series with one another, it's like one capacitor with twice the distance between it is really what happened. So if I put them in series, what I'm going to do, I'm going to have less capacitance. If I add more to the circuit, add more capacitors to the circuit in series, I'm going to have less. It's actually an inverse effect. More capacitors in series are going to have a less capacitive effect. And it's because what it does, it's like a plate of the same size, only twice the distance between it, like I've shown you right here. See? So I'm going to have less capacitive effect. Remember, we talked about the distance between the plates determines the value of the capacitor. This series has an effect of adding a greater distance between my plates. So I'm going to have less capacitive effect. Okay? Now, in parallel, when I put them in parallel, what'll happen now, if I have two capacitors in parallel, now what I'll do, I'll add them. See? To get my total capacitance, I would add them, because it's like one capacitor of twice the plates, you see. In other words, you see each side has more plate area. So now when I have them in parallel, I'll add their effects to get the total capacitance. Now what we're going to do in our circuits coming up now, the next step is to apply these components to an alternating current circuit. What we're after now is what opposition to current flow is created by the inductor and the capacitor. So we'll move on to that point.